Good morning everyone. Alhamdulillah, we're going to discuss here the third lesson, magnetism. Okay, if you have any doubts on first lesson and second lesson, come and meet me in person. Okay, I will clarify everything within this week. After that, the next week on 5th, we're going to write about the first lesson, full lessons. Okay, read well and write well. Inshallah, after that lessons, I will give some feedback. Okay, so this week we are seeing about the magnetism. Okay, what is a magnet and what are the magnetic properties? Now, see, this is a bar magnet. Okay, so there are type of magnets which is artificial magnet as well as natural magnets. Okay, these are called artificial magnets. Here we have the bar magnet, and here look at there's one point is on the bar magnet which is directed or which is noted as a north pole. Okay, say next one, the Coulomb's inverse square law. Coulomb inverse square law. What is meant by Coulomb? We know that Coulomb's force, right? What is meant by Coulomb force? The force of attraction or repulsion between any two charges is directly proportional to product of the charges and inversely proportional to square of the distance between them. Same here, the Coulomb inverse square law is discussed for magnetic field. Okay, magnetic magnets. So whenever there is a two magnets, whether they attract or repel, okay, the like poles are repel and unlike poles are attract. Now, if there is the force of attraction or repulsion between the any two poles is directly proportional to product of the pole strength, and inversely proportional to square of the distance between them. Inversely proportional to square of the distance between them. So then the magnetic force is equal to KQMA R square. What is the value of K? The K is called proportionality constant, and K will be equal to mu naught times of 4 pi. Mu naught times by 4 pi. Now, what is the value of mu naught? Mu naught is nothing but 4 pi into 10 power minus 7 Henry per meter. Now, what is that magnetic field along the point along the axis? Okay, along the axial line. A magnetic dipole. What is meant by dipole? When the pole strength, okay. See, I have the magnet or bar magnet, which is at the south pole. Here I have the north pole. Here I have the center. Here I have the point where I have to find the magnetic field. Okay, same whatever things you did in the first lesson. That's it. From the center, the distance of the P will be located as let it be R. Okay, the length of the magnetic poles will be 2L. So here the L and here 1L. From the north pole to south pole, the magnetic field lines will be moved inside the dipole moment, magnetic moment. Okay, inside the dipole magnetic moment. Now, we have to calculate what is the magnetic field along due to the point N, or let it be the point C. I will say P. Let A be the poles, which is separated by a distance of 2L, and then the P is located on the point along the lies on the north pole in the x-axis or axial line. Okay, now the magnetic field due to the north pole. Magnetic field due to the north pole. What is meant by magnetic field force by experienced by the unit magnetic pole strength? So K2R mu naught by 4 pi Q by or QM or QA. QM, okay, QM by the R square. R square is nothing but the total distance minus this distance. Then only I can know this distance, right? So R minus L whole square. R minus L the whole square. So the magnetic field due to the south pole, mu naught by 4 pi QM, the total distance R plus L. So it will become R plus L the whole square. Okay. Now, what is the total magnetic field? The total magnetic field, due to the north pole, we have to take in the account of negative. Okay, negative. So it will become negative. The total magnetic field will be equal to Bn by Bs. Okay, Bn plus Bs. Now what will happen? The total magnetic field B will be equal to mu naught by 4 pi is a common. Take it outside. 2m also common. Take it outside. 1 by R minus L the whole square minus 1 by R plus L the whole square. Okay, cross multiply. mu naught by 4 pi qm r plus l the whole square minus r minus l the whole square divided by a minus b whole square, a plus b whole square. It will become a square minus b square. Okay, that's it, right? Now, as usual, whatever the things you have did for that electrical field, okay? Mu naught qm by 4 pi a plus b whole square formula, a square plus b square plus 2ab minus a square plus b square minus 2ab by r square plus r square minus l square, right? Now, as usual, what to do? The total magnetic field will be equal to mu naught qm by 4 pi. Multiplying inside that, it will become negative, and it will become positive. R square, L square will be cancel each other. So 2RL, 2RL. It will become 4RL divided by R square minus L square. Okay, now listen. We can write this 4RL as mu naught qm by 4 pi 2 into 2RL by r square minus l square. Okay, whenever we are comparing the length of the when you are comparing the length of the L, when you are comparing with this r, the L will become much more lesser than. So L is much more lesser than r, so L square can be neglected. So what will happen if the L square will be neglected? So it will become, the total magnetic field will become mu naught qm by 4 pi 2 into 2RL divided by r power 4. So 1r will be cancelled. 2L into qm. 2L into qm is nothing but a dipole moment. Okay, magnetic dipole moment. So mu naught 2 dipole moment, magnetic moment divided by 4 pi r cube. So this is the magnetic field along the axial line. Okay, the next one, the magnetic field due to the equator line. Same, what are the things you have learned in the first lesson, it will be repeated. Okay, so there we are using the A, here we are using the L, that's it. Now, due to that equator line, so what will happen? That dipole will be here, magnetic field, now south pole, north pole, here we have the point. So let O be the center, the distance of R will be located, and we have the 2L, distance of 2L, and we have the point, here the magnetic moment will be take place in the 4 directions. The 2 sin theta component will be cancelled, cos theta component will be added. Okay, due to the north pole, BN magnetic field due to the north pole will get mu naught by 4 pi qm r. Okay, here we have the L, here we have the R. So R square will become R square plus L square, right? Let it be R dash. Okay, R dash will become R square plus L square. So R square plus L square. So due to the south pole, it will become minus mu naught by 4 pi qm divided by R square plus L square. Now again same thing, mu naught qm by 4 pi take outside, 1 by R square plus L square minus R minus L square. But here the total magnetic field added and represented by 2 components, sin theta components and the cos theta components. Okay, so what will happen? The cos theta components will be added. You can take any one of that. Okay, because Bn will be equal to Bs, right? Bn will be equal to Bs. So both the equations will be equal. So we can take any one of them, and then the total magnetic field will be equal to we can take anything Bn cos theta. So what is that cos theta? Cos theta is nothing but adjacent by hypotenuse. Adjacent by hypotenuse. Here we will get mu naught by 4 pi qm r square plus l square. What is that adjacent here? The theta will be acting here. Okay, theta will be acting here. What is the adjacent? Adjacent will become L divided by r root of r square plus l square. Becomes r dash square will be equal to r square plus l square. Then r will be equal to root of r square plus l square, right? Okay. R square plus l square. Now, r square plus l square power 1, r square plus l square power 1 by 2. So it will become the distance of adjacent by hypotenuse, right? So it will become L by r square plus l square. So qm into 2l, right? It will become qm into 2l by r square plus l square. So both are equations are left. Okay, Bn will be equal to Bn. So when the magnitude will be equal to Bn plus Bs. So 2Bn we can take. Right. So when you are taking Bn will be equal to Bs. So we can take this one. So 2 times of Bs. So here we can take 2. Okay. Now 2 mu naught qm by 4 pi root of r, you can take r square plus l square power 3 by 2. R square plus l square power 3 by 2. Now we can take this integral, right? So 2l qm is nothing but the magnetic dipole moment. So mu naught pm divided by 4 pi r square plus l square power 3 by 2. If the l square is much more longer than r, so r is much more greater than l, then it will become l square will become neglected. L square will become neglected. Okay, then it will become B total magnitude will become mu naught pm by 4 pi r cube. This is due to equator line. This is due to equator line. Okay, so the magnetic field due to the axial line will become equal to mu naught by 4 pi to magnetic dipole moment divided by r cube. So B equals here, magnetic field due to the equator will be equal to mu naught by 4 pi dipole moment, magnetic dipole moment by r cube. So the same here, the B axial, the magnetic field due to the axial line equal to 2s of the B equatorial. 2s of the B equatorial. Okay, so this is very important another 5 mark. Okay, axial line and as well as equator line. Now next one, the torque acting on the bar magnet. What will happen if the torque acting on the same thing? What happened? The dipole is placed in the uniform electric field. Same thing when the north pole or south pole, and the bar, magnetic bar is placed on the uniform magnetic field. Okay, consider this is your uniform magnetic field. Here I have the bar magnet, which is on the south pole, and here are the north pole. Here the point we have, the total force will be acting on this point, QB, right? Here positive side. Here I have the force on the minus QB. Here are the point 0, I mean O, L, L. So the total distance will be 2L. Okay. Here are the point C. Now, what is the torque? The torque is nothing but any one of the force into perpendicular distance. Any one of the force into perpendicular distance. So here I have the Fn and here I have the Fs. Okay, force on the south side and the force on north side. So Fn plus what will happen? The total force Fn will be this is O and this is Cs, right? Cs plus Fs into minus of from the center CV. Okay, CV. AB will be this one. Then Fn L sin theta plus Fs L sin theta. So what is that? 2B L sin theta Okay, QM, let it be QM. QM B sin theta. So it's nothing but 2QM B L sin theta. So 2L QM will become magnetic moment. So PM B sin theta. PM B sin theta. Now the task will be equal to, we can write the sign as a cross product, so we can write this one also like this. Okay, so when the theta equal to 0 degree and the theta equal to 0 degree, the torque will become equal to 0. The torque will become equal to 0. When the theta equal to 90 degree, the torque will become maximum. The torque will become maximum. That's it. Okay. The next one, the potential energy of the bar magnet in the uniform magnetic field. The potential energy of the bar magnet in a uniform magnetic field. Same thing. Okay. Here, what will happen? See, work done per unit deflection. Work done per the small amount of work done per unit deflection will be equal to torque. So the work done will be equal to torque into d theta. Now the total amount of work done will be equal to integration of dw. So it's nothing but integration of dou into d theta. So it will become integration of PMB sin theta into d theta. So if I integrate this sin theta into d theta, what will happen? It will become cos theta minus cos theta. So the total work done will be equal to minus PMP cos theta. Now this work done as stored as the potential energy of the bar magnet. U will become minus PMP cos theta. When it's parallel, okay, when the bar magnet parallel to the uniform magnetic field, theta equals 0 degree, then it will become minimum. It will become minimum. When it's anti-parallel to the uniform magnetic field, theta equal to 180 degree, so it will become maximum. So when it's perpendicular to the direction of potential, it will become 0. That's it. This is also one of the important 3 mark question. The next one, the next last but not least is very important. What is mean by magnetic properties? What is mean by magnetic properties? First one. See, this is a bar magnet, right? So here I have the one specimen. Is nothing but your well pins. Now what will happen? It is attracted by that magnet, right? It is attracted by the magnet. Now that bell pins are magnetizing by this magnet. Okay. Now the bell pin magnetizing by this magnet or bar magnet. That also works on the principle and also is attracted. They have some attractive properties because this bell pin is magnetized by this magnet and this one is magnetized by this bell pin. Okay. These specimens are magnetized by this other magnet is called magnetizing field. Okay. Now the magnetic field which is used to magnetize the sample or specimen is called magnetizing field. This is a vector quantity. And then magnetic permeability. How much of magnetic field can permit by that specimen? It is called magnetic permeability. It is called magnetic permeability. The magnetic permeability is the measure of ability of the material to allow the passage of magnetic field and through it or measure the capacity of the substance to take magnetization or degree of penetration. The relative permeability mu r is defined as ratio between the absolute permeability of the medium to the permeability of the free space. Permeability of the free space. We know that already. Mu r will be equal to absolute by free space, right? Mu equal to mu naught into mu r. There we are using epsilon r equal to epsilon by epsilon naught. Here we are using mu naught. Okay. Intensity of the magnetization. The magnetization in any bulk materials. Okay. What is meant by magnetization or intensity of the magnetization? Intensity of magnetization is nothing but how much of magnetic moment per unit volume. Magnetic moment per unit volume. This is called magnetic intensity or intensity of magnetization. The net magnetic moment per unit volume of the material. Okay. So what will happen? Magnetic moment also we can write the product of current and the area. Okay, current and the area. magnetic induction or total magnetic field. The magnetic induction inside the specimen equal to the sum of the magnetic field produced in the vacuum due to the magnetizing field and the magnetic field due to the induced magnetism of the substance. Okay, the total magnetic field on the substance or specimen. When you are considering the bell bearings, what is the total magnetizing field acting on the specimen? Is nothing but the earth magnetism and then magnetism applied on the objects. That's it. Okay, that is called free space. Okay, magnetic susceptibility. As a ratio of the intensity of the magnetization induced in the material to the magnetizing field, the sign will be equal to how much of magnetizing fields are applicable to the magnetic field by the magnetic field. Okay, how much intensity of magnetization induced in the material by the magnetizing field. Okay. So based on these properties, there are a lot of materials are classified. So there are the three types of materials. This is called dia, para, ferro material. Dia, para, ferro material. Which are the susceptibility lows? They are called dia material, dia magnetic material. Okay. See, diamagnetic material. In the presence of uniform external magnetic field, some electrons are speeded up and some are slowed down. The electron whose movements are anti-parallel speeded up according to the Lenz's law, and this produces an induced magnetic movement in the direction of the opposite field. The induced movement disappears as soon as electric field is removed. Okay, some material, when the external magnetic field is applied on that material, there are anti-parallel movement. They have the anti-parallel movement. That kind of materials will be known as the diamagnetic material. Okay. Then when the place in the non-uniform magnetic field, the interaction between the induced magnetic movement and the external field creates the force which tends to move the material from the stronger part to weaker part. From the stronger part to weaker part. This type of action we call as this action is called diamagnetic action. These materials are known as diamagnetic materials. Examples are bismuth, copper, and then water. Okay. Next one. What is the properties of diamagnetic material? What is the properties of diamagnetic material? They have the low susceptibility, low reactivity. Okay, relative permeability is slightly less than unity. That means lesser than 1. The magnetic field lines are repelled and expelled by the diamagnetic when placed in the uniform field. Susceptibility is nearly temperature dependent. And then the next one is paramagnetic material. They have the magnetic moment inside. When you are applying the external field, they have the random motion. When you are applying that, they are aligned in the direction of the magnetic field. So this kind of action we call the paramagnetic action. These properties we call as material which behaves these properties we call the paramagnetic materials. Okay. They have the properties of magnetic susceptibility is positive and small. Relative permeability is greater than unity. That means greater than 1. The magnetic field lines are attracted into the paramagnetic materials when it is placed in the magnetic field. Susceptibility is inversely proportional to the temperature. Curie's law. When the temperature increases, thermal vibration will upset the alignment of the magnetic dipole moment. Therefore, magnetic susceptibility decreases with it. Magnetic susceptibility decreases with the temperature increases. This law is known as Curie's law. The ferromagnetic materials. Okay, inside that domain. Inside the domains, all have the dipole moment aligned with parallel, but all the domains have the random direction. When they have applied the external field, all the domains have the same in the parallel to one another. So the domains having the magnetic moment parallel to the field grow bigger in size. The other domains are rotated that they are aligned with the magnetic field. So this kind of material behaves ferromagnetic actions. Okay, when placed in the non-uniform magnetic field, the ferromagnetic materials will have the strong tendency to move from weaker point to stronger point. Weaker part to the stronger one. Magnetic susceptibility is positive and large, and then permeability is very large, and magnetic field are strongly attracted to the ferromagnetic materials when they are placed in the magnetic field. Susceptibility is inversely proportional to the temperature. And here we have to discuss one law, which is called Curie-Weiss law. What is that? Curie-Weiss law. What is the Curie-Weiss law? As the temperature increases, ferromagnetic material decreases due to the increased thermal emission. Okay. So some materials at particular temperature, the ferromagnetic materials behaves like a paramagnetic material. So that kind of magnetic behavior we call as Curie's temperatures, and this law we known as Curie-Weiss law. Curie-Weiss law. Okay. And also there is one. There is given 146. Magnetism plays interesting role in the various aspects of life. It has connection with the archaeologist place Keelady too. Okay. To find whether the archaeology structure exists under the surface of given place, well-established techniques are called magnetometer survey is used. In this technique, the variation of the magnetic field in comparison with the neighboring place is studied. The magnetic field variation is due to the presence of the mineral magnetic and is related minerals present in the archaeology structures like buried watery and then bricks and buried domes and movements and inhabited sites. Those minerals are either diamagnetic or paramagnetic or ferromagnetic in nature, and each type has a different range of magnetic susceptibilities. IIG, that is Indian Institute of Geomagnetism, Mumbai, has conducted magnetometer survey on Keelady site and found that there were archaeology structures like pottery, etc. From the picture 1, figure 1, there was a magnetic field variation ranges 10 to 100 nanotesla over the particular area. In fact, the existence of massive brick structures or Keelady has been revealed through the magnetism. Okay. Based on these magnetic behaviors, the spin and the mass also will be discussed. Okay, like mass and charge for the particle, spin also another important attribute for the elementary particle. Spin is the quantum mechanical phenomenon which is responsible for the magnetic properties of the material. Different from the spin in the quantum mechanics is entirely different from the spin we encountered in the classical mechanics. Spin in the quantum mechanics does not mean the rotations. It is instantaneous angular momentum which does not have the classical analog. For historical reason, the name spin is retained. The spin of the particle takes only the positive values, but the orientation of the spin vector takes plus or minus values. In an external magnetic field, for an example, the electron has a spin of s equal to 1 by 2. In the presence of magnetic field, the spin will orient either parallel or anti-parallel to the direction of the magnetic field. It implies that magnetic spin takes the true values for the electron, such as ms will be equal to 1 by 2 spin up, m by 2 will be equal to minus 1 by 2, ms will be equal to minus 1 by 2 spin down. Spin for the proton and neutron equal to 1 by 2 for proton, spin s equal to 1. The type of magnetism, page number 148, there is a type of magnetism. Compare that types of magnetism. So read out this, not for the examination, but you can understand the behavior of dia, para and ferromagnetism. Okay, so next one is hysteresis is nothing but what? Hysteresis is nothing but how much of it is the magnetic field or the lagging of magnetic induction behind that magnetic field. Okay, behind that magnetic field. Even though, for example, I will give this example. Okay, see, now when I am having the bar magnet, it is now magnetizing. Okay, the magnetic induction takes place after some times. Okay, when I am removing this magnetic induction, this bell pin is having some kind of magnetizing field. Okay, which is attracted another properties, another objects. Okay, are specified. It is called hysteresis loop or hysteresis, lagging behind the magnetic induction. Okay. Okay guys, Allah Hafiz. For this week this is enough. Next week I will teach. We'll go for the Byron's law and remaining things. Okay. Thank you. Allah Hafiz.